picture this for a moment. You're standing in your backyard on a clear night, looking up at that gorgeous ribbon of light we call the Milky Way stretching across the sky. It's beautiful, isn't it? That faint glow represents our entire galactic neighborhood, home to somewhere between 100 and 400 billion stars. Your mind starts wandering, and you think to yourself, wow, this galaxy is absolutely massive. There's no way anything could be bigger than this cosmic city we call home. But here's where things get mind-bending in ways that will literally reshape how you see your place in existence. What if I told you that our entire galaxy, with all its hundreds of billions of stars, all its spiral arms stretching 100,000 light years across, is nothing more than a single grain of sand on an endless beach? What if everything you think you know about the scale of space is so wildly off that it's like comparing a marble to planet Earth? Tonight, we're going on a journey that's going to completely shatter your perception of scale. We're going to explore just how impossibly, ridiculously, mind-crushingly huge the universe actually is compared to our little galactic home. And I promise you, by the end of this exploration, you'll never look at the night sky the same way again. Now, before we dive into this cosmic comparison that's gonna blow your mind, let me give you some context about what we're dealing with here. Most people have absolutely no idea just how big space really is. They hear numbers like billions and trillions thrown around, but these numbers are so large that our brains literally can't process them in any meaningful way. It's like trying to count every grain of sand on every beach on Earth while blindfolded. But here's what makes this even more incredible. Not only are we going to compare the size of our galaxy to the entire universe, but I'm going to show you visual analogies and mathematical breakdowns that will help you actually grasp these impossible scales. We'll explore how many Milky Ways could fit inside the observable universe, what the universe would look like if our galaxy was the size of a coin, and why this comparison reveals something absolutely profound about our existence. And trust me, the numbers we're about to discuss are so staggering that they make winning the lottery look like a certainty. We're talking about scales that involve more zeros than you've probably ever seen in your life. But first, let's establish our cosmic baseline. What exactly are we comparing here? Our galaxy, the Milky Way, is what astronomers call a barred spiral galaxy. It's got these beautiful spiral arms that curve out from a central bar-shaped structure, and the whole thing is roughly 100,000 light years in diameter. That means if you could travel at the speed of light, it would take you 100,000 years just to cross from one side of our galaxy to the other. Now, a light year isn't just some arbitrary unit astronomers made up to sound cool. 1 light year represents the distance that light travels in a vacuum over the course of 1 year. And since light moves at about 186,000 miles per second, we're talking about roughly 6 trillion miles in a single light year. So when we say our galaxy is 100,000 light years across, we're talking about 600 quadrillion miles from edge to edge. Let me put that in perspective for you. If you could drive a car at highway speeds across our galaxy without stopping, it would take you over 700 billion years to make the trip. That's about 50 times longer than the universe has even existed. The numbers are already getting pretty wild, and we haven't even started talking about the universe yet. Our galaxy contains somewhere between 100 and 400 billion stars. That's billion with a B. If you tried to count every star in our galaxy at a rate of 1 star per second, it would take you over 3,000 years just to finish counting. And remember, each of these stars could potentially have its own planetary system, its own worlds, maybe even its own forms of life. But here's where things start getting really interesting. Our galaxy isn't just sitting alone in empty space. It's part of what's called the local group, which is basically our galactic neighborhood. The local group contains about 80 galaxies, including our closest major neighbor, the Andromeda Galaxy, which is actually about 2.5 times larger than the Milky Way. And the local group itself? It's just one tiny cluster in something called the Virgo supercluster, which contains over 1,300 galaxies. But even that massive structure is just one supercluster among thousands of others scattered throughout space. Now, are you ready for this? Because we're about to scale up to the universe, and your brain might actually hurt from trying to process what I'm about to tell you. The observable universe, which is the part of the universe we can actually see and measure, has a diameter of approximately 93 billion light years. Wait, hold on. I know what you're thinking. If the universe is only about 13.8 billion years old, how can the observable universe be 93 billion light years across? Shouldn't it be more like 27.6 billion light years if light has been traveling for 13.8 billion years in each direction? Here's the thing that breaks most people's brains. Space itself has been expanding since the Big Bang. So while light from the most distant galaxies has been traveling toward us for nearly 13.8 billion years, those galaxies have been moving away from us the entire time due to the expansion of space itself. When we account for this expansion, the most distant objects we can observe are now about 46.5 billion light years away in each direction, giving us that 93 billion light year diameter. But even this mind-boggling number might be just the tip of the cosmic iceberg. The observable universe is just the part we can see. The actual universe could be infinite, or it could be so large that calling it infinite wouldn't be much of an exaggeration. So now, let's get to the comparison that's going to completely reshape your understanding of scale. How big is the universe compared to our galaxy? If we took our entire Milky Way Galaxy, with its 100,000 light-year diameter and its hundreds of billions of stars, and we shrank it down to the size of a grain of sand, then the observable universe would be roughly the size of a football field. But that's actually being conservative. Some calculations suggest that if our galaxy was a grain of sand, the observable universe would be more like the size of North America. Let me give you another way to think about this. Imagine you could take every single star in our galaxy and line them up in a row. Remember, we've got somewhere between 100 and 400 billion stars to work with. Now, how many Milky Way galaxies do you think would fit inside the observable universe? The answer is going to make your head spin. Based on current estimates, there are roughly 2 trillion galaxies in the observable universe. That's 2 trillion separate galactic cities, each potentially containing hundreds of billions of stars. If we assume an average galaxy size similar to our own, we're looking at somewhere between 200 sextillion and 800 sextillion stars in the observable universe. What's a sextillion? It's a 1 followed by 21 zeros. To put that in perspective, if every star in the observable universe was a grain of sand, you'd have enough sand to bury the entire surface of the Earth under a layer that's several miles deep. But here's what really breaks your brain. All of these mind-crushing numbers we've been talking about, all of these impossible scales and incomprehensible distances, they only apply to the part of the universe we can actually observe. The real universe, the total universe, could be vastly larger than what we can see. Some cosmological models suggest that the entire universe could be at least 250 times larger than the observable universe. Other models propose that space could be truly infinite, extending forever in all directions with no edge or boundary. If the universe is infinite, then our galaxy isn't just small compared to the universe. It's infinitesimally small. It's so small that mathematically speaking, it takes up 0% of the total space available. An infinite universe would contain an infinite number of galaxies, an infinite number of stars, and an infinite number of worlds. Think about that for a moment. In an infinite universe, every possible arrangement of matter would not only exist somewhere, but it would exist an infinite number of times. There would be infinite copies of our galaxy, infinite versions of our solar system, and infinite versions of you reading this right now. But let's step back from infinity for a moment, because even without it, the comparison between our galaxy and just the observable universe is staggering enough to fundamentally change how you think about your place in the cosmos. Here's another way to visualize this scale. If you could somehow travel at the speed of light, it would take you 100,000 years to cross our galaxy from edge to edge. But to cross the observable universe at light speed, that journey would take you 93 billion years. That's nearly 7 times longer than the universe has existed. The volume difference is even more extreme. Our galaxy occupies a volume of space that's roughly equivalent to a sphere about 100,000 light years in diameter. The observable universe occupies a sphere that's 93 billion light years in diameter. When you calculate the volume ratio, you find that the observable universe is roughly 800 million times larger than our galaxy in terms of the space it occupies. To put that in everyday terms, if our galaxy was the size of a marble, the observable universe would be roughly the size of the Earth. And remember, that's just the part we can see. Now let's take this mind-bending comparison even further, because we're just getting started on this journey into cosmic perspective. When astronomers try to map out the structure of the universe, they discover something that makes this size comparison even more incredible. Galaxies aren't just randomly scattered throughout space, like someone threw cosmic confetti into the void. They're organized into an enormous web-like structure that spans the entire observable universe. Think of it like a three-dimensional spider web, except instead of silk strands, you've got filaments made of dark matter and galaxies stretching across billions of light years. These cosmic filaments can be over 500 million light years long, connecting massive galaxy clusters that contain thousands of individual galaxies. Between these filaments are vast empty regions called cosmic voids, some of which are so empty that they contain virtually no galaxies at all across distances of hundreds of millions of light years. Here's what really breaks your brain about this cosmic web structure. Our entire local group, which includes the Milky Way, Andromeda, and about 80 other galaxies, is just a tiny speck sitting on one of these cosmic filaments. The filament we're riding on is part of something called the Laniakea supercluster, which spans about 520 million light years and contains roughly 100,000 galaxies. But get this, even Laniakea, with its 100,000 galaxies and mind-crushing 520 million light-year span, is just one small neighborhood in the cosmic web. There are thousands of other superclusters scattered throughout the observable universe, each containing tens of thousands of galaxies. Let me give you another analogy that might help your brain process this insane scale. Imagine our galaxy is a single house in a neighborhood. Our local group would be like the block that house sits on. The Virgo supercluster would be like the city containing that block. But Laniakea? That would be like an entire country. And the observable universe would contain millions of these cosmic countries, each filled with their own cities, neighborhoods, and houses. Now here's where things get even more mind-bending. Remember how I mentioned that there are roughly 2 trillion galaxies in the observable universe? Well, that number keeps changing as our telescopes get better and we can peer deeper into space. When the Hubble Space Telescope first started making deep observations, astronomers thought there were maybe 100 billion galaxies in the observable universe. Then better observations suggested 200 billion. More recent studies, using improved techniques, have pushed that number up to 2 trillion, and some researchers think it could be even higher. Each time we discover more galaxies, we're essentially finding more grains of sand on that cosmic beach I mentioned earlier. And every single one of these galactic grains contains billions or even trillions of stars, each potentially hosting their own planetary systems. But here's something that will really make your head spin. When we look out into deep space, we're not just looking across distance, we're looking back in time. Light from distant galaxies takes billions of years to reach us, which means we're seeing these galaxies as they existed billions of years ago. The most distant galaxies we can observe appear as they were when the universe was less than 1 billion years old. These ancient galactic babies are much smaller and more chaotic than modern galaxies like our own. They're still in the process of forming, with massive star-forming regions blazing across their relatively tiny structures. This means that as we look deeper into space and further back in time, we're essentially watching the universe grow up. We can observe cosmic evolution happening on the grandest possible scale, watching as tiny protogalaxies merge and grow into the massive galactic structures we see in the local universe today. And here's something that might blow your mind even more. Some of those distant, ancient galaxies we're observing have since evolved, merged with other galaxies, and grown into massive structures that could be hundreds of times larger than what we're currently seeing. But their light from their current state won't reach us for billions more years. This means the universe we observe isn't even the universe as it exists right now. It's a patchwork of cosmic history, with nearby objects showing us the recent past, and distant objects showing us the ancient past. The universe as it exists today, right now, in this very moment, is something we can never directly observe except for our immediate cosmic neighborhood. Think about how this affects our size comparison. Those 2 trillion galaxies we can observe, many of them have been growing, merging, and evolving for billions of years since the light we're seeing first left them. The actual current universe could contain structures and galaxies far larger than anything we can currently observe. Let's dive deeper into what this means for the density of stuff in space. You might think that with 2 trillion galaxies spread across 93 billion light years, space would be pretty crowded. But you'd be wrong in the most spectacular way possible. The average density of matter in the observable universe is roughly 5 protons per cubic meter. That's emptier than the best vacuum we can create in laboratories here on Earth. If you took a cube of space the size of a house and removed all the air, you'd still have far more matter in that empty house than exists in an equivalent volume of intergalactic space. This means that even though the universe contains an incomprehensible number of galaxies, stars, and planets, it's still mostly empty space. Vast, mind-numbing amounts of empty space stretching between the cosmic structures we've been talking about. Those cosmic voids I mentioned earlier can span hundreds of millions of light years and contain virtually nothing. Imagine flying through space for 500 million years at the speed of light and seeing almost no galaxies, no stars, no nothing. Just endless darkness punctuated by the occasional lonely galaxy drifting through the void. But here's where our cosmic perspective gets really wild. Even with all this empty space, even with the incomprehensible distances between galaxies, the observable universe is still expanding. Space itself is stretching, carrying galaxies away from each other at velocities that increase with distance. Galaxies that are currently about 14 billion light years away from us are moving away at roughly the speed of light due to cosmic expansion. Galaxies even further out are receding faster than light itself. This doesn't violate Einstein's speed limit because the galaxies aren't moving through space faster than light. Space itself is expanding and carrying them along. This cosmic expansion means that the universe is getting bigger every second. As you've been reading this, the observable universe has grown by millions of miles in every direction. Distant galaxies have moved millions of miles further away from us. The cosmic web has stretched just a tiny bit more. And here's the kicker. This expansion appears to be accelerating. Something called dark energy, which makes up roughly 68% of all the energy in the universe, is driving space to expand at an ever-increasing rate. This means that billions of years in the future, the universe will be even more mind-bogglingly huge than it is today. Galaxies that we can barely see today will eventually be carried so far away by cosmic expansion that their light will never reach us. Future civilizations looking out into space will see a much lonelier universe with fewer visible galaxies and vast stretches of apparently empty space. But let's bring this back to our original comparison, because I want to make sure the scale of what we're discussing really sinks in. We started by comparing our galaxy to the observable universe, but let's think about what this means for us as individuals. If our galaxy is like a grain of sand on a cosmic beach, then our entire solar system would be smaller than a single atom within that grain of sand. Earth would be so small within this analogy that it wouldn't even register as a subatomic particle. And you would be so impossibly, incomprehensibly tiny in this cosmic comparison that there isn't a word in any human language to describe how small you are relative to the universe. You're not just a drop in the ocean. You're smaller than a single molecule in a drop in an ocean that spans multiple continents. Yet here's the beautiful paradox that makes all of this so profound. Despite being unimaginably small in the cosmic scheme of things, you're also incredibly significant. You're a complex arrangement of atoms that can contemplate the very universe that contains you. You're made of star stuff, forged in the nuclear furnaces of ancient suns and scattered across space by cosmic explosions. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created inside stars that lived and died billions of years ago. You are literally made of the universe, and through your consciousness, the universe is experiencing itself. But let's take this mind-bending journey even deeper, because what we've discussed so far is just scratching the surface of how truly incomprehensible the universe's scale really is. When cosmologists try to measure the universe, they run into something called the horizon problem, and it's going to make everything we've talked about seem quaint by comparison. Here's the thing that keeps astronomers awake at night. The observable universe, that 93 billion light-year sphere we've been discussing, represents an absolute limit to what we can ever hope to see. But the actual universe beyond that boundary could be so large that our observable portion is like a single drop of water in all the Earth's oceans combined. Current inflation models suggest that during the first fraction of a second after the Big Bang, space expanded so rapidly that regions now separated by vast distances were once in contact. This cosmic inflation could have stretched the universe to proportions that make our observable bubble seem microscopic in comparison. Some calculations suggest the entire universe could be at least 10 to the power of 23 times larger than what we can observe. That's not 23 zeros, that's 23 zeros after the number 1. If you wrote that number out in standard notation, it would take you several minutes just to write all the zeros. To put this in perspective, if the observable universe was the size of a proton, the actual universe might be larger than a basketball, and that's potentially a conservative estimate. Other models suggest the universe could be truly infinite, extending forever in all directions with no edge or boundary whatsoever. Now here's where your brain is really going to start hurting. If the universe is infinite, then everything we've been discussing about scale becomes even more mind-crushing. An infinite universe would contain infinite galaxies, infinite stars, infinite planets, and infinite copies of everything that could possibly exist. Think about what infinite really means. In an infinite universe, there wouldn't just be another galaxy exactly like the Milky Way somewhere out there. There would be infinite copies of our galaxy, infinite copies of our solar system, and infinite copies of you having this exact same realization about cosmic scale right now. But let's step back from infinity for a moment and focus on something we can actually wrap our heads around, sort of. Even if we just stick to the observable universe, the numbers involved in our galactic comparison are so staggering that they challenge the very limits of human comprehension. Remember those 2 trillion galaxies scattered throughout observable space. Each one of those galaxies is roughly comparable to our own Milky Way in terms of size and stellar population. That means we're looking at somewhere around 200 sextillion stars in total. That's 2 followed by 23 zeros. If you wanted to count all the stars in the observable universe at a rate of 1 per second, it would take you longer than the age of the universe multiplied by 10 million. The universe would have expanded so much during your counting session that many of the stars you started counting would have moved beyond the edge of the observable universe before you finished. But here's something that makes this comparison even more incredible. Those stars aren't just randomly distributed throughout space. They're organized into galaxies, which are organized into galaxy groups, which are organized into clusters, which are organized into superclusters, which are organized into the cosmic web we talked about earlier. This hierarchical structure means that the universe isn't just big, it's organized on scales that dwarf our galaxy in ways that are almost impossible to visualize. The cosmic web filaments that connect galaxy clusters can stretch across distances that are thousands of times larger than our entire galaxy's diameter. Imagine if our Milky Way was a single street lamp in a city. The cosmic filaments would be like highways connecting cities that are thousands of miles apart, and the entire observable universe would contain millions of these cosmic metropolitan areas, each connected by a vast network of matter and energy flowing across billions of light years. Now let's talk about something that's going to make this size comparison even more mind-bending. When we observe distant galaxies through our most powerful telescopes, we're not just seeing static objects sitting peacefully in space. We're witnessing a universe in constant motion, with structures forming, evolving, and interacting across cosmic time. Galaxy collisions are happening throughout the universe right now. Massive galactic structures containing trillions of stars are crashing into each other at speeds of millions of miles per hour, creating new stellar formations and reshaping the cosmic landscape on scales that make our entire galaxy look like a tiny pebble in an avalanche. Our own galaxy is actually on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor. In about 4.5 billion years, these two massive stellar cities will merge in a cosmic collision that will fundamentally reshape our local galactic neighborhood. The resulting merged galaxy, sometimes called Milkomeda, will be roughly 5 times larger than our current Milky Way. But here's the incredible thing about this impending galactic collision. Even though it involves hundreds of billions of stars from both galaxies, the chances of any two stars actually colliding during this merger are virtually zero. The distances between individual stars are so vast that the entire galactic collision will happen around them without direct stellar impacts. This gives you another sense of the incredible scales we're dealing with. Even within our own galaxy, space is so empty that a collision involving hundreds of billions of stars will likely result in 0 actual stellar collisions. The stars will just rearrange themselves into new orbital patterns around the combined gravitational center of the merged galaxy. Now, let's zoom out even further and think about what this means for our cosmic comparison. If galaxy collisions involving hundreds of billions of stars are relatively common events throughout the universe, then the dynamic nature of cosmic structure formation operates on scales that make our static view of our home galaxy seem almost quaint. Throughout the observable universe, there are probably millions of galaxy mergers happening right now. Massive elliptical galaxies are forming through the collision of smaller spiral galaxies. New star formation is being triggered by gravitational interactions between galactic neighbors. Supermassive black holes at galactic centers are merging, releasing gravitational waves that ripple across space-time itself. All of this cosmic drama is playing out simultaneously across those 2 trillion galaxies we discussed earlier. The universe isn't just unimaginably large, it's also incredibly active and dynamic on scales that span the entire observable cosmos. But here's something that might blow your mind even more than the size comparison itself. The universe we can observe represents a sphere centered on Earth, which means we're seeing ourselves as the center of the observable cosmos. But this is just an illusion created by the finite speed of light and the age of the universe. Every point in the universe has its own observable sphere surrounding it. An alien civilization in a galaxy 10 billion light-years away would see their own 93 billion light-year diameter observable universe centered on their location. Most of their observable universe would contain galaxies that we can't see from Earth, and most of our observable universe would be invisible to them. This means that the total number of galaxies that exist within the broader universe is potentially much larger than the 2 trillion we can observe from our cosmic vantage point. We're each seeing our own unique slice of a much larger cosmic pie. Think about what this means for our galactic comparison. If there are regions of the universe that we can't observe, filled with galaxies we can't detect, then our grain of sand analogy might be even more dramatic than we initially thought. Our galaxy might be like a grain of sand on a beach that extends far beyond the horizon in every direction. But let's bring this back to something that might help you really grasp these incomprehensible scales. The light from the most distant galaxies we can observe has been traveling toward us for over 13 billion years. When that light first began its journey toward Earth, our solar system didn't even exist yet. The sun was still part of a giant molecular cloud that wouldn't collapse to form our star for another 9 billion years. This means that we're literally seeing the universe as it existed before our solar system was born. Some of the galaxies we observe in deep space images existed when the universe was less than 1 billion years old, when the first generation of stars was just beginning to forge heavy elements in their nuclear cores. Those ancient galaxies appear much smaller and more chaotic than modern galaxies like our own. They were still in the process of assembling themselves from smaller proto-galactic fragments, with massive bursts of star formation creating brilliant stellar nurseries across their compact structures. Yet even these ancient, relatively small galaxies were already enormous by any reasonable standard. A typical early galaxy might have been only 10,000 light-years across, which seems tiny compared to our 100,000 light-year Milky Way. But 10,000 light-years still represents a distance so vast that light takes 10,000 years to cross it. And here's the thing that really breaks your brain. Many of those distant, ancient galaxies we're observing have since grown and evolved into massive modern galaxies that could be several times larger than our own Milky Way. But because their light takes billions of years to reach us, we're seeing them as they were in their cosmic youth, not as they exist today. The universe, as it exists right now, in this very moment, contains structures and galaxies that are potentially much larger than anything we can currently observe. Our size comparison between the galaxy and the universe might actually be conservative because we're comparing our current galaxy to a universe that we can only see as it existed in the past. Some of those 2 trillion galaxies we counted have probably merged with their neighbors over the past few billion years, creating even more massive galactic structures. Others have continued growing through ongoing star formation and accretion of intergalactic material. The current universe might contain far fewer but much larger galaxies than what we can observe. This temporal aspect of cosmic observation adds another layer of complexity to our scale comparison. We're not just comparing our galaxy to the universe as it exists today, we're comparing it to a patchwork of cosmic history that spans nearly the entire age of the universe, and that brings us to perhaps the most profound aspect of this entire comparison. The universe we observe isn't static, it's expanding, evolving, and growing larger every single second. As space itself stretches, carrying galaxies away from each other, the cosmic structures we've been discussing are being stretched across ever greater distances. This means that the universe tomorrow will be measurably larger than the universe today. The cosmic web filaments will be slightly longer, the voids between galaxy clusters will be slightly emptier, and the most distant galaxies will be slightly further away. In a very real sense, the universe is growing around us as we speak, making our galactic grain of sand seem even smaller with each passing moment. The beach our cosmic grain sits on is expanding in all directions, creating more space for more cosmic sand grains that we haven't discovered yet. And if current models of cosmic expansion are correct, this growth will continue accelerating for billions of years into the future, creating a universe so large that it makes our current cosmic perspective seem as limited as believing the Earth was the center of everything. The comparison between our galaxy and the universe isn't just about size. It's about recognizing that we exist within a cosmic system that operates on scales so vast and timescales so long that they challenge the very foundations of how we understand our place in existence. Yet somehow, through the power of human curiosity and scientific observation, we've managed to measure and map this incomprehensible cosmic arena. We've figured out that our galactic home, vast as it seems to us, is just one tiny component in a universal symphony that spans distances and contains structures that dwarf our wildest imagination. But here's where this cosmic comparison takes on an even more staggering dimension that's going to make everything we've discussed so far seem almost manageable. We've been talking about the observable universe as if it's the whole story, but there's something called the multiverse hypothesis that suggests our entire universe might just be one bubble in an infinite foam of universes. Think about that for a moment. If our galaxy is like a grain of sand on the beach of our universe, and if the multiverse theory is correct, then our entire universe might be like a single grain of sand on an infinite beach of universes. Each universe potentially containing its own 2 trillion galaxies, its own cosmic web structures, its own physics and fundamental constants. Some versions of multiverse theory suggest there could be an infinite number of parallel universes, each slightly different from our own. Others propose that new universes are constantly being created through a process called eternal inflation, where space itself spawns new cosmic bubbles at an exponential rate. Under these models, the comparison we've been making between our galaxy and our universe becomes just the first layer of an infinitely nested hierarchy of scales. Our galaxy compared to our universe compared to the multiverse, and potentially even higher levels of organization that we haven't even conceived of yet. But let's step back from these mind-melting theoretical extremes and focus on something we can actually measure and observe. Even within our single universe, there are cosmic structures that make our galaxy seem microscopic in ways we haven't fully explored yet. The largest known structure in the observable universe is something called the Hercules Corona Borealis Great Wall. This cosmic filament stretches across roughly 10 billion light-years of space. That's about 1/9 the diameter of the entire observable universe, and it's roughly 100,000 times larger than our entire galaxy. To put this in perspective, if our Milky Way was the size of a marble, the Hercules Corona Borealis Great Wall would be roughly the size of Manhattan. This single cosmic structure contains millions of galaxies connected by invisible threads of dark matter, creating a web-like pattern that spans distances so vast they defy human comprehension. And here's what really breaks your brain about structures like this. The Great Wall isn't just big, it's so big that light from one end takes 10 billion years to reach the other end. That means if someone at one end of this structure sent a message to someone at the other end, traveling at the speed of light, it would take longer for that message to arrive than our entire solar system has existed. But the Great Wall is just one example of these massive cosmic structures. Throughout the observable universe, there are countless other filaments, walls, and superclusters that dwarf our galaxy by factors of thousands or millions. Our local group, which seemed pretty impressive when we first discussed it, would be like a single house on a street that's millions of miles long. Now let's talk about something that's going to add another layer of mind-bending complexity to our cosmic comparison. When astronomers try to map out these massive structures, they discover that the universe has a kind of fractal quality, where patterns repeat at different scales. Just like our galaxy has spiral arms that branch out from a central structure, the cosmic web has filaments that branch out from massive galaxy clusters. Just like our solar system has planets orbiting the sun, our galaxy orbits around the center of mass of our local group. Just like our local group is part of a larger cluster, that cluster is part of an even larger supercluster. This hierarchical organization continues all the way up to the largest scales we can observe. It's like a cosmic Russian nesting doll, where each level of organization contains smaller versions of similar structures. The patterns that govern the formation of our solar system are echoed in the patterns that govern the formation of galaxy clusters billions of light years across. What this means for our size comparison is that our galaxy isn't just small compared to the universe, it's small at every level of cosmic organization. We're small compared to our local group, which is small compared to our cluster, which is small compared to our supercluster, which is small compared to the cosmic filaments, which are small compared to the observable universe. And here's something that might make this hierarchical scaling even more incredible. The same physical processes that shaped our galaxy are operating at every level of this cosmic hierarchy. Gravity pulls matter together into increasingly larger structures. Rotation creates spiral patterns and stable orbits. Magnetic fields channel the flow of gas and plasma across vast distances. The physics that governs how stars form in our galaxy is fundamentally the same as the physics that governs how galaxies form in clusters, which is fundamentally the same as the physics that governs how clusters form into superclusters. The universe is using the same basic toolkit to build structures across scales that span more than 20 orders of magnitude. Let me give you another way to visualize just how extreme this scaling really is. If you could somehow shrink yourself down to the size of an atom, the scaling between you and a human would be roughly similar to the scaling between our galaxy and some of the largest cosmic structures we've discovered. But here's where it gets even weirder. At the quantum level, space itself might have structure that we're only beginning to understand. Some theories suggest that at the smallest possible scales, space and time might be made up of discrete units, like pixels on a cosmic computer screen. If these theories are correct, then the scaling we've been discussing continues all the way down to the fundamental fabric of reality itself. The same universe that contains structures 10 billion light years across might be built from components that are trillions of times smaller than an atomic nucleus. This means we exist at a kind of middle scale in a cosmic hierarchy that spans from the smallest possible units of space and time all the way up to structures that approach the size of the entire observable universe. We're like beings living on the surface of a fractal pattern that extends both infinitely inward and infinitely outward. Now let's think about what all of this scaling means for the flow of time itself. We've been talking about distances and sizes, but the temporal scales involved in cosmic evolution are just as mind-crushing as the spatial scales. Our galaxy takes roughly 240 million years to complete one rotation. That means since the first dinosaurs appeared on Earth, our solar system has completed less than one full orbit around the galactic center. The last time we were in our current position relative to the galaxy's spiral arms, life on Earth consisted mostly of single-celled organisms. But galactic rotation is just the beginning of cosmic timescales. Galaxy clusters take billions of years to form and evolve. The cosmic web filaments we discussed earlier have been growing and connecting for most of the universe's 13.8 billion year history. Some of the largest cosmic structures are so young in cosmic terms that they're still in the process of assembling themselves. This temporal perspective adds another dimension to our size comparison. Our galaxy isn't just small in space, it's also operating on timescales that are tiny compared to the evolution of cosmic structure. While our galaxy completes hundreds of rotations, the massive cosmic filaments barely have time to grow measurably larger. Think about what this means for cosmic evolution. The universe we observe today is just a snapshot of an ongoing process of structure formation that operates on timescales billions of times longer than human civilization has existed. The cosmic web is still growing, still connecting distant regions of space, still channeling matter and energy across distances that dwarf our galaxy. And here's something that might blow your mind about these cosmic timescales. The most distant galaxies we can observe appear as they were when the universe was less than 1 billion years old. But the universe is expected to continue existing for trillions of years into the future, potentially even longer. This means that we're observing the universe during what might be considered its early childhood. The cosmic structures we see today will continue growing and evolving for thousands of times longer than the universe has already existed. Our galaxy is not just small in the current cosmic hierarchy, it's small during what might be the smallest phase of cosmic evolution. Future civilizations, billions of years from now, will inhabit a universe where galaxies have merged into massive elliptical structures, where star formation has slowed dramatically, where the cosmic web has stretched so much that individual filaments become nearly impossible to detect. The universe they observe will be fundamentally different from the one we see today, but there's something even more profound about our temporal position in cosmic history. We happen to exist during the only epoch when the universe is transparent enough for us to observe distant galaxies, yet young enough that those galaxies haven't been carried beyond our observable horizon by cosmic expansion. Earlier in cosmic history, the universe was filled with hot, opaque plasma that blocked light from traveling freely through space. Much later in cosmic history, accelerating expansion will have carried most galaxies so far away that they'll fade beyond detection. We exist during a brief cosmic moment when the universe is perfectly configured for astronomical observation. This temporal sweet spot makes our size comparison even more remarkable. Not only are we tiny compared to the cosmic structures we can observe, but we exist during the relatively brief period when such observations are even possible. We're like microscopic organisms who happen to have evolved eyes during the few moments when their environment is illuminated. And that brings us to perhaps the most profound aspect of this entire cosmic comparison. Despite being unimaginably small in both space and time compared to the universe around us, we've somehow developed the ability to measure and understand these incomprehensible scales. Through telescopes and mathematics, through physics and computation, we've managed to map cosmic structures that are billions of times larger than anything our ancestors could have imagined. We've traced the history of cosmic evolution across nearly the entire age of the universe. We've discovered our place within hierarchies of organization that span from quantum scales to cosmic horizons. The atoms in our brains, forged in the cores of ancient stars, have organized themselves into patterns capable of contemplating the very cosmic processes that created them. We are the universe becoming aware of itself, studying its own structure and evolution through the emergence of consciousness on tiny rocky planets orbiting ordinary stars and unremarkable galaxies. Our galaxy may be nothing more than a grain of sand on an infinite cosmic beach, but within that grain of sand, the universe has developed the capacity to understand its own immensity. Through us, the cosmos has learned to measure itself, to trace its own history, to contemplate its own future evolution across timescales that dwarf the existence of any individual observer. The comparison between our galaxy and the universe reveals something more profound than just a difference in scale. It reveals that size and significance operate by completely different rules. The smallest components of the largest system have somehow become capable of comprehending the whole. The most temporary phenomena in the most enduring cosmos have developed the ability to perceive cosmic permanence. We exist at the intersection of the infinitely large and the infinitely small, the eternally ancient and the momentarily present. Our brief lives play out against a backdrop of cosmic structures so vast and ancient that they seem like the architecture of eternity itself. Yet somehow, through the emergence of consciousness and curiosity, these cosmic scales have become not just observable, but comprehensible. The universe may be unimaginably larger than our galaxy, but our galaxy has produced something that the universe, for all its vastness, cannot produce without us. The capacity for wonder, the drive to explore, the ability to find meaning and beauty in the very immensity that makes us seem so small. This is the true significance of our cosmic comparison. Not that we are small, but that smallness has somehow become capable of grasping greatness. Not that we are brief, but that brevity has learned to perceive eternity. Not that we are insignificant, but that significance emerges from the most unlikely corners of an infinite cosmos. And this realization leads us to something even more staggering about cosmic perspective. When we think about consciousness emerging from cosmic processes, we're not just talking about a rare accident that happened to occur on one small planet. We're talking about the universe literally waking up to itself through billions of years of stellar nucleosynthesis, planetary formation, and biological evolution. Every carbon atom in your DNA was forged inside a dying star. Every oxygen molecule you breathe was created when massive stars exploded and scattered their enriched cores across space. The calcium in your teeth, the iron in your blood, the phosphorus in your thoughts, all of it emerged from cosmic processes operating on the scales we've been discussing. But here's where this gets absolutely mind-bending. Those stellar factories that created the elements of life weren't just operating in our galaxy. They were operating simultaneously in trillions of other galaxies across the observable universe. Right now, as you're processing these words, there are countless stellar explosions happening across cosmic distances, creating and distributing the raw materials for consciousness. This means that the process that led to your existence isn't unique to our little corner of space. It's happening everywhere, all the time, across every one of those 2 trillion galaxies we discussed. The universe isn't just unimaginably large, it's also unimaginably fertile, constantly creating the conditions for complexity and awareness to emerge. Think about what this implies for our cosmic comparison. If consciousness can emerge from stellar processes, and if stellar processes are happening throughout the universe, then consciousness might be emerging everywhere. Our galaxy might be just one of countless galactic neighborhoods where the universe is developing the ability to understand itself. Some researchers estimate that there could be billions or even trillions of planets in our galaxy alone that are capable of supporting complex chemistry. If even a tiny fraction of those worlds develop consciousness, then our Milky Way could contain millions or billions of different perspectives on cosmic scale. Now multiply that by 2 trillion galaxies, and you're looking at a universe that might be teeming with conscious observers, each trying to comprehend the same incomprehensible scales we've been discussing. Each one discovering that their home galaxy is tiny compared to the cosmic structures around them. each one experiencing that same vertigo-inducing shift in perspective when they realize how vast their universe really is. But here's something that adds another layer of profound strangeness to this cosmic comparison. The observable universe we've been discussing isn't just the limit of what we can see, it's also the limit of what we can ever hope to influence or interact with. Those distant galaxies at the edge of our observable horizon are receding from us so fast due to cosmic expansion that no signal we could ever send would reach them. Even if we developed technology that allowed us to travel at the speed of light, we could never visit most of the cosmic structures we've been discussing because space itself is expanding faster than we could traverse it. This means that the vast majority of the universe we can observe will forever remain beyond our reach. We can study it, measure it, contemplate its immensity, but we can never touch it or influence it in any meaningful way. We exist in a kind of cosmic isolation bubble, connected to the broader universe only through the ancient light that reaches our telescopes. Yet paradoxically, this isolation makes our cosmic neighborhood even more precious. Our local group of galaxies represents not just our galactic home, but the entire region of space that we could ever hope to explore or influence. Everything beyond that cosmic horizon might as well be in another universe entirely. Within a few billion years, cosmic expansion will have carried most observable galaxies beyond our detection threshold. Future civilizations will look out into space and see a much lonelier cosmos, with vast stretches of apparently empty space where we currently observe rich galaxy clusters and cosmic web structures. This temporal evolution of cosmic structure adds yet another dimension to our size comparison. Not only is our galaxy tiny compared to the current universe, but the universe itself is constantly changing in ways that will eventually make even our current perspective seem quaint. The cosmic web filaments that currently span billions of light years will stretch and thin until they become undetectable. Galaxy clusters will disperse as space expands. Even our own local group will eventually merge into a single massive elliptical galaxy, isolated in an ever-expanding ocean of empty space. From this perspective, we exist during what might be called the golden age of cosmic observation. The universe is old enough to have developed complex structures and conscious observers, yet young enough that those structures remain visible and accessible to study. We're living during the brief cosmic moment when the universe has become self-aware through conscious beings like ourselves, but before cosmic expansion has hidden most of its structure beyond our observational horizon. We're experiencing cosmic consciousness during the only epoch when such consciousness has something truly spectacular to contemplate. This temporal aspect makes our galaxy's relationship to the universe even more poignant. We're not just small grains of sand on a cosmic beach. We're small grains of sand that have developed eyes during the brief period when that beach is illuminated by cosmic light. But let's zoom back out to the largest scales one more time, because there's something about cosmic structure that we haven't fully explored yet. The universe isn't just big and expanding, it's also incredibly uniform on the largest scales, yet incredibly lumpy on smaller scales. When cosmologists measure the temperature of the cosmic microwave background radiation, the afterglow of the Big Bang, they find that it's uniform to within 1 part in 100,000. This means that regions of the universe separated by billions of light years have almost exactly the same temperature and density. Yet when we look at smaller scales, we see enormous variations in density. Galaxies are millions of times denser than the average cosmic density. Galaxy clusters are thousands of times denser than the space between them. The cosmic web creates a foam-like structure with dense filaments separated by vast empty voids. This combination of large-scale uniformity and small-scale structure tells us something profound about how the universe evolved. The tiny quantum fluctuations present in the early universe were stretched by cosmic inflation to become the seeds of all the cosmic structures we observe today. Our galaxy exists because of quantum mechanical uncertainties that existed when the universe was smaller than an atomic nucleus. The cosmic web filaments that dwarf our galaxy by millions of times grew from fluctuations so small that they were governed by Heisenberg's uncertainty principle. This means that the scale comparison we've been making between our galaxy and the universe is fundamentally connected to the smallest scales of physics. The largest structures in the universe grew from the smallest possible fluctuations in the fabric of spacetime itself. In a very real sense, our galaxy is simultaneously connected to both the largest and smallest scales in nature. We exist at an intermediate scale in a cosmic hierarchy that spans from quantum uncertainty to cosmic horizons, from the Planck length to the observable universe. This connection between scales makes our cosmic comparison even more remarkable. We're not just comparing two different sizes, we're comparing different levels of a single, unified system that connects quantum mechanics to cosmology, particle physics to galactic structure, the smallest possible scales to the largest observable features. The atoms in our bodies participate in quantum interactions that operate on scales trillions of times smaller than atomic nuclei. Yet those same atoms are organized into structures that can contemplate cosmic filaments billions of light years across. We exist at the intersection of quantum mechanics and cosmology, embodying the universe's capacity to bridge scales that differ by more than 60 orders of magnitude. And here's something that might be the most mind-bending aspect of this entire cosmic comparison. The universe appears to be mathematically describable at every scale we've discussed. The same equations that govern the motion of planets around stars also govern the motion of stars around galactic centers and galaxies around cluster centers. The same physical constants that determine how atoms bond to form molecules also determine how gravity pulls cosmic matter into the web-like structures we observe on the largest scales. The universe seems to be built from a surprisingly small set of fundamental principles that manifest in endlessly complex ways across every possible scale. This mathematical unity suggests that our galaxy and the universe aren't just connected by scale, they're connected by the same underlying physical laws and principles. The forces that hold our galaxy together are the same forces that organize cosmic structure across billions of light years. From this perspective, our cosmic comparison reveals something deeper than just size differences. It reveals that we live in a universe where the same fundamental patterns repeat at every scale, where consciousness emerges naturally from cosmic processes, where the smallest components can understand the largest structures. Our galaxy may be tiny compared to the universe, but it's also an integral part of the cosmic web that gives the universe its structure. We may be brief compared to cosmic timescales, but we're also the means through which the universe experiences its own history and contemplates its own future. The comparison between our galaxy and the universe ultimately reveals not our insignificance, but our profound connection to cosmic processes operating on every possible scale. We are simultaneously cosmic dust and cosmic consciousness, temporary patterns in an eternal dance, small parts of an infinite whole that has somehow learned to perceive its own infinity. In the end, perhaps the most remarkable thing about our cosmic comparison isn't how small we are, but how vast our capacity for understanding has become. We've learned to measure the unmeasurable, contemplate the incomprehensible, and find meaning in scales that transcend any practical human experience. We exist as conscious patterns in a universe that stretches across scales so vast they challenge the very concepts of size and significance. Yet somehow, from our tiny galactic grain of sand, we've learned to see the entire cosmic beach and recognize our place within it. The universe may be unimaginably larger than our galaxy, but our galaxy has produced minds capable of imagining that unimaginable vastness. And perhaps, in the end, that capacity for wonder and understanding is the most cosmic thing of all. But there's something even more staggering that we need to explore about this cosmic comparison, something that's going to completely redefine what it means to think about scale in the universe. We've been talking about the observable universe as if it's this massive, incomprehensible sphere of space containing 2 trillion galaxies. But here's what's going to blow your mind. The observable universe might actually be the smallest possible sample of what's really out there. Think about this for a moment. Every calculation we've made, every mind-bending comparison between our galaxy and the cosmos has been based on what we can actually see. But the universe doesn't stop at the edge of our vision. It keeps going, potentially forever, in ways that make our already impossible numbers look like child's arithmetic. Current cosmological models suggest that the total universe beyond our observable bubble could be at least 1,000,000 times larger than what we can detect. Some theories push this even further, proposing that our observable universe represents such a tiny fraction of total reality that comparing it to the whole would be like comparing a single atom to planet Earth. Let me put this in terms that might help your brain process what we're really dealing with. If our Milky Way Galaxy was the size of a bacteria and the observable universe was the size of Earth, then the total universe might be the size of our entire solar system. We're not just talking about bigger numbers here. We're talking about levels of scale that completely redefine what the word big even means. Now here's where things get really wild. Within this potentially infinite expanse of space, the patterns we observe in our local cosmic neighborhood are probably repeating everywhere. That cosmic web structure we discussed, with its filaments spanning billions of light years? There could be millions or billions of similar web structures scattered throughout regions of space we'll never see. Remember those 2 trillion galaxies in our observable universe? If the total universe is even moderately larger than what we can observe, we're looking at quadrillions or quintillions of galaxies existing in regions of space that will forever remain beyond our detection, each one potentially harboring billions of stars, trillions of planets, and countless opportunities for complexity and consciousness to emerge. But let's dive even deeper into what this means for our cosmic perspective. The expansion of space isn't just carrying distant galaxies away from us, it's also revealing new regions of space that were previously beyond our observational horizon. Every second, our observable universe grows slightly larger as light from more distant regions finally has enough time to reach us. This means that the universe is constantly revealing new galaxies, new cosmic structures, new regions of space that we've never seen before. Right now, as you're processing these words, light from galaxies billions of light years away is crossing the boundary into our observable universe for the first time in cosmic history. We're not just living in an expanding universe, we're living in a universe that's constantly revealing new layers of its own vastness. Every day brings new cosmic territory into our field of view, expanding our perspective on scales that were literally invisible the day before. Yet even as our observable universe grows, cosmic expansion ensures that we're simultaneously losing contact with regions of space that are being carried beyond our reach. The universe is simultaneously revealing new mysteries while hiding others forever beyond our cosmic horizon. This creates a kind of cosmic paradox. The more we discover about the universe's true scale, the more we realize how much we'll never be able to discover. Every answer reveals dozens of new questions. Every measurement of cosmic vastness hints at even greater scales lurking beyond our detection capabilities. Now let's think about what this means for the emergence of consciousness and intelligence throughout the cosmos. If the universe is truly vast beyond our current comprehension, filled with countless galaxies and stellar systems, then the process that created consciousness on Earth is probably happening everywhere, all the time, across scales that dwarf our wildest imagination. Consider this possibility. Within our observable universe alone, there could be billions of civilizations grappling with the same cosmic perspective we're exploring right now. Countless minds on countless worlds, each discovering that their home galaxy is tiny compared to the universe around them, each experiencing that same vertigo-inducing shift in perspective when they realize the true scale of cosmic reality. But if the total universe extends far beyond what we can observe, then consciousness might be emerging not just in billions of locations, but in numbers so large that they challenge our understanding of what infinity really means. We might be part of a cosmic community of conscious beings that spans scales and regions of space so vast that our entire observable universe represents just one tiny neighborhood in an infinite cosmic city. This perspective transforms our galactic comparison from a story about cosmic loneliness into a story about cosmic connection. Our galaxy isn't just a tiny grain of sand on an empty beach. It's potentially one grain among infinite others, each supporting its own forms of awareness, creativity, and wonder. So here we are, standing at the edge of the ultimate cosmic perspective, having journeyed from our backyard view of the Milky Way to the mind-crushing realization that our entire galaxy is nothing more than a microscopic speck in an ocean of unimaginable vastness. We've discovered that if our galaxy was a grain of sand, the observable universe would be the size of a football field, and the total universe might extend infinitely beyond even that incomprehensible scale. We've learned that consciousness itself might be emerging everywhere throughout this cosmic expanse, creating a community of awareness that spans scales so vast they redefine what it means to exist. The next time you step outside and look up at that beautiful ribbon of the Milky Way, remember that you're not just seeing our galactic home, you're seeing the launching point for one of the most profound realizations in human history. You're witnessing the universe contemplating itself through your own consciousness, proving that sometimes the smallest things can grasp the greatest mysteries.